All right. Our last talk before we get to the panel is by Vitalik, who's going to tell us about the future of Ethereum.
Great. Okay, so today I'm going to, I'll also try my best to make this shorter than what I did yesterday in San Francisco, but I'm going to talk about base layer blockchain scaling and try to give a kind of more precise understanding of basically what is it that makes scaling blockchains and specifically scaling blockchains to the point where they process more transactions than what one single computer can process, a very difficult problem. And particularly later on, I'm going to talk about something called the data availability problem, which turns out to be one of the main challenges in doing this sort of thing. So to start off, just to introduce a bit of notation, this is called a blockchain. It contains blocks. Every block contains transactions. Those arrows represent every block containing the hash of the previous block. Everyone still following? Now, I'm gonna use this number C to represent the computational capacity of a node. So C is basically the quantity of the number of transactions that a node can process. I mean, we'll say per second, we can say per block interval, either in terms of computation or in terms of storage requirements or in terms of bandwidth. We just assume that all of these are proportional and roughly equivalent to each other. And in a simple chain, we'll also say that the transaction capacity of the network is also going to have to be O of C. And the reason for this is simple, because if the transaction capacity of a network is greater than than O of C, then that means that nodes can't process all the transactions, nobody can run a full node, and so the blockchain doesn't work anymore, right? So there's a few incomplete ways to scale a blockchain. So all of these are technically scaling solutions, but they all come with serious drawbacks. So here's the first one. Super big blocks, right? So increasing block sizes definitely does have its place, and I think there's definitely a lot of cases where you can get quite a lot just by increasing a few constants up. But if this is your only scaling strategy and you try to push it to the limit, then you have a problem. So the problem basically is that if we increase this from C to 1,000 times C, then okay, the network capacity goes up from C to 1,000 times C. You've increased your transactions per second by a factor of 1,000, but the load on each validator also goes up by a factor of 1,000. So the amount of transactions that each node has to process only goes up by a factor of 1,000. But we've made an assumption already that this is larger than the amount of transactions that a regular computer can process, and so your only nodes are going to be inside of data centers. So this is strategy number one. This is strategy number two, and this is kind of the strategy that the crypto space has already been implicitly going towards, whether intentionally or not, right? So Bitcoin transaction fees, in many cases over $1, sometimes over $5. Well, okay, fine, use Bitcoin Cash. Well, Bitcoin Cash transaction fees go higher, well, use Ethereum. Well, if Ethereum transaction fees go higher, use Ethereum Classic. Ethereum Classic transaction fees go higher, we'll use Doge. Doge transactions are still cheap, right? So, basically just keep going, and if we get to quote mainstream adoption, we'll be going all the way down the list until we get to making transactions in coins with names like Trump Coin and Project Decorum. So this is technically a scaling solution, right? And this gives you a network capacity of 1,000 times C. The validator load is only C, because it's every user only really needs to be a node on one blockchain, and that each individual blockchain is still only going to have O of C capacity. The problem is each and every one of these chains is going to have 1,000 times the lower security. So if you look at Trump Coin, well, the market cap is something like $600,000. Well, probably any single one of you could basically, if you really wanted to, afford the money to personally run a 51% attack on their blockchain. So, this is this is the second approach. Now, merge mining is another approach, and this basically says we have 1,000 altcoins, but we let people mine many altcoins at the same time. The problem is this also doesn't solve the problem, and the reason is that you have the main parameter that you can adjust here is like on average how many altcoins does each miner end up mining. If the number is close to 1, then you're not actually gaining much security. Each individual altcoin is still 1,000 times easier to attack than it was before. But if you're going, if the number is very high, so if the number is close to all of them, then basically miners still have to process every transaction until you've actually done basically the exact same thing as this, except technically it's split up into 1,000, but like the data structure is slightly different, but the effect is basically the same. So it looks like we have a scalability trilemma here, right? So the trilemma claims that, look, now this is not an absolute fact, right? And as I'm going to later claim, there are ways to get around this, but it's very hard to get around this. And the trilemma claims that blockchain systems can only have, at most, 2 of the following 3 properties. So the first property is decentralization, and intuitively it basically means the network can run as long as entirely on the basis of random ordinary guys with laptops. Right? This is the definition of decentralization. The next, so basically you do not require data centers, you do not require like super nodes, you do not require any, basically any particular kind of, cluster of that, or any one category of user to have, like more special status that other users do not. Scalability, defined as being able to process more transactions than a laptop can process. So in this case, O of n, in computer science notation, O of n greater than O of c. And security, being secure against attackers with up to O of n resources. And the best way to interpret this is basically being secure against attackers that have up to some fixed percentage of the network. So you have 51% attack for a naive proof of work attack, or you have 51%. You have 34% to break asynchronous Byzantine fault-tolerant consensus. You have 0 to 34%, or 25% with the fix to do selfish mining attacks, and so on and so forth. So, what you're not allowed to have is a security bounds that goes down, or an attack threshold that goes down and down the higher the scalability goes, right? So it's actually fairly easy to get 2 out of these 3. So we can have decentralization and security with a simple blockchain, like Bitcoin and Ethereum as they exist today. We can have scalability and security with super big blocks. And we can have decentralization and scalability with 1,000 altcoins. Can we have all 3? Well, this gets very tricky. So we're going to take a bit of a detour into something called interactive computation, or sometimes interactive verification. So the setup for the interactive verification game is like this. Let's suppose that you have some function some long computation that you're trying to make. And this computation is, something that just takes an extremely long amount of time. So, but it has the property that it's a function that can be decomposed into a large number of different functions, where if you start off with some input x, and the function itself becomes a composition, so f is a composition of fn minus 1 all the way down to f1. So if you look at all the intermediate values, f1 of x, then the value after f2, the value after f3, every single intermediate value is also basically very small in size. So specifically at most O of c in size. So if you have a computation that has this property that it's just a long string of a value being strung through a chain of functions, where at every step along the way the value remains small, then we can play this simple kind of game, and basically we can kind of trustlessly compute the value of f using a blockchain as a verification aid, but without doing everything on the blockchain. So here's the first step. The submitter is going to process, take x and run through f1, f2, f3 all the way down to fn, and the submitter is going to send a transaction, which is like a solution candidate, right? And the solution candidate is going to contain, it's obviously going to contain y, the answer, but It's also going to contain S1, which is the value that you get after you take X and you apply F1 to it. S2, so S1 but applying F2 to it. S3, so S2 but applying F3 to it, and so on and so forth. All the way down to Sn, which is basically the same thing as Y. Now, the submitter also, so it sends a transaction. A transaction contains all these intermediate values, and the submitter submits this along with a deposit. So first of all, we can immediately tell right now, if this scheme works, what is the maximum computational complexity of F that can be processed. So if this is done inside of a simple blockchain, then the blockchain has OFC capacity. So, the gas limit is OFC. And first of all, later on, we are going to depend on the ability to compute any FI inside the blockchain. So the computational complexity of each individual FI can only be OFC. And because we have to submit all of these in one transaction, the number of these S values, and so the number of F values, is also going to have to be at most OFC. OFC multiplied by OFC means that F can have a complexity of at most OFC squared. So what's the next step here? Once the submitter submits the solution candidate, there is some challenge period. This could be an hour, could be a day, could be a week, could be 5 minutes if you're feeling really daring. Within this challenge period, anyone can submit a challenge index. And a challenge index is basically saying, hey, look, this particular solution is wrong, and it's wrong right over here. So if, for example, you see, some computation, and you just decide to randomly audit it, and let's say you randomly audit, you go and you take the value S42 that got submitted, and you just personally try to apply F43, and you notice that the S43 value that you compute is not the same as the S43 value that the guy submitted. So you notice that there was an error in the submission. You can send a challenge transaction, and as one of the arguments to the challenge transaction, so this is going to be calling a function, it has the argument, and the argument is going to be this index 43. Now what happens then is that the contract actually is going to execute in this case F43 inside the EVM, inside consensus, and it's going to execute it on S42, and it's going to see if it actually gets the same S43 that was supplied in the transaction. If it was, then you're just raising a false alarm and you get nothing and you just wasted a huge pile of gas. But if it turns out the contract notices that this particular answer that was submitted actually is wrong, then the challenger gets some portion of the submitter's deposit, and this is the incentive for people to do this kind of auditing. If no challenges are made within some challenge period, then the submitter gets the deposit back, the submitter gets a reward, and the system kind of assumes that the submission is correct. So this is kind of the basic idea behind interactive computation. Now, you can actually extend this, and there's two ways to extend it. So the first way is that if you want to turn this into, if you want to increase the capacity from OFC squared to OF2 to the power of C, so make it exponential, then you can play this multi-step game where basically the submitter submits 3 values, and then the challenger has to say either you're wrong on the left or you're wrong on the right, and then the challenger has to provide the value in the middle. Then the submitter can kind of contest the challenge and say either you're wrong on the left or you're wrong on the right, and so you do this sort of interactive binary search until eventually you get down to the bottom, and on the bottom you do it on-chain. So you can do this sort of thing. And another thing that you can do is you can also actually extend interactive computation so that it works with computations where the values in the middle are too big to basically bigger than OFC. So you can't put an entire intermediate result onto the blockchain all at once. And the way you do this is with Merkle trees. So when I presented this in San Francisco, it required everyone to bow to Ralph Merkle, so I'll require everyone here to do the same. So everyone should be really thankful for this guy because, it really is, who here has synced an Ethereum Lite client? Who here has synced a Geth full node at any time in the last year? Parity node. all of you have saved hundreds of gigabytes of bandwidth because of this guy. Okay, so for those who don't know what Merkle trees are, basically they allow for efficiently verifiable proofs that basically some piece of data is a member of some much bigger piece of data. So if you want to make this much more abstract, you can assume that, let's say you're having 1 megabyte file, you're going to make this kind of complicated hash construction out of the 1 megabyte file, and eventually you're going to create it's going to have a 32-byte root hash at the top. And so what you might want to do later is you might want to prove that some particular value is in some particular position in the original data when the original data is kind of publicly represented by the root hash. So what you do is you basically have all of these hashes, and basically you provide the Merkle proof, or sometimes called the Merkle branch, is just a set of hashes that goes from the root specifically down the chain, going along this kind of path to the specific value that you're trying to give a proof of. And so someone can check the proof basically by checking that the hashes match up at every step along the way, and if they match up, then the proof is correct. Now, if someone tries to create a false value and make a Merkle proof of a false value, then at some point the hashes are not going to match up. So this is what Merkle proofs do. Now, the idea basically is that, and Merkle trees actually get used a lot in Ethereum, and the other major use case in Ethereum is that they get used for the state tree, right? So the state in Ethereum is basically the set of all accounts and the set of all contract storage for all contracts. So basically all of the kind of information that you would need to have in order to process and verify transactions and just know what the state of things is right now. Now, this is stored in this kind of special hash tree, and any particular state, it can be represented by this 32-byte root hash that we call the state root. And so state roots are, basically uniquely mapped to the state. And so if I have the state root, then theoretically I can use that to authenticate the entire state. So all of the accounts, all of the every single piece of storage and every single contract, all of the balances. But in order to authenticate any individual piece of the state, I would need a Merkle branch. And the Merkle branch basically just is the hashes going down from the root all the way down, down along some particular path in the tree. So the way that we can think about fraud proofs is that fraud proofs kind of are an application of interactive computation to verifying the blockchain. So, but here is kind of what I mean by this. So you can think of verifying an entire blockchain. So verifying a blockchain, from Genesis to 4.39 million, where it is right now, as kind of like being an f, like this f function, right? So it's an f that decomposes into f1.fn very naturally. X is the Genesis state. And we can think about the state as being the state root, right? So you can kind of think about the state here as just being the root hash. F1 is apply the first block to the Genesis state. What is the state after that? F2 is take the state after block 1 and apply block 2. F3 is apply block 3, and so on and so forth until Fn is apply like the last block in the chain. So right now block close to 4.29 million. Now, there is one important difference here, though, between verifying a blockchain and this simpler case that we talked about earlier. So with verifying a blockchain, right? So first of all, what do we know what can we kind of allow users to have, right? So you can require light clients to download every single block header. Right, so every block has this piece of data at the top called the block header, and the block header's purpose is basically to contain a reference to the previous block and to contain a whole bunch of data and to contain root hashes. So a hash of the transaction tree, a hash of the and a hash of the state the root hash of the state after processing all those transactions. So we can assume that every let's say we have a type of user, a light client, that can download all of these block headers, but they do not have enough capacity to download and process all of the blocks. And so what we do is we're going to basically do a kind of a very similar thing. What we're going to say is that a light client is just going to actively listen on the network for challenges. And what is a challenge? Well, a challenge basically says block, in this chain that you got, block number 3,849,223 is wrong. Now, the main difference here, though, is that because you're operating over large sets of transactions, and because you're operating over large states, and the light client by itself is not going to store the state, and it's also not going to download all of the transactions, basically a challenge has to also provide witness data. So what do we mean by witness data? Basically, the light client already has all the block headers, and so the light client has the Merkle tree root of the transactions in the blocks and of the state after processing each block. So you can think of that as being like these SI values. But what they do not have is that the light client does not have the actual transactions, and the light client does not have any portion of the state in any block. These are values that the light client can authenticate if you provide them with Merkle branches, but these aren't values that the light client has yet. And so a challenge has to be not just a challenge index, but also witness data, right? Also the Merkle branches that allow that basically tell you, this is the actual set of transactions in this particular block, and this is the portion of the state that was modified by this particular block, so that the light client can actually run through all the computations and check whether the state root after processing the block is correct or incorrect. So because you're operating on these large sets of data, and because it's not like from the kind of light client's point of view, it's not a pure computation, it's this kind of computation that keeps on constantly accessing this extra data from the outside, you have to, challenges also have to provide this witness data as well. Now, so what is a fraud proof? Basically, a fraud proof is a challenge index plus all of the witness data, so the transactions and the kind of branches in the state that you need to execute a particular block. And so a light client can execute, if it receives a challenge, it can actually verify only that particular block, and it can check for itself whether the block is actually valid or not. Now, this is so far theoretically doable, but there is a problem, and the problem is data unavailability attacks. So data unavailability attacks are basically attacks where a malicious miner creates or publishes a block that the block header is present, but some or all of the block data is missing, right? So you can think of this as being a block that has 8 transactions. Well, the first transaction here, it could be a valid transaction. It could be an invalid transaction, but whoever published the block is not publishing it, right? So now, first of all, what can data unavailability attacks do? What is the worst that can happen because of a data unavailability attack? The first thing that the attack can do is it can convince the network to accept invalid blocks. And particularly, there's no way to prove invalidity, right? So this transaction over here could be a valid transaction, or it could be an invalid transaction that gives me 50 million ether out of nowhere. If you do not have the data, you have no way of verifying which is which. And technically, in an information theoretic sense, there's basically an infinite number of valid transactions that have the same hash, so it really could be any of them, and there's also an infinite number of invalid transactions that have the same hash, so it could be any of those. So that's the first thing that you can do. But now you might think, oh well, you may have heard of weird, spooky, fancy math called ZK snarks, zero knowledge proofs, or ZK starks. And these basically let you prove that a block is valid, and to let you prove that or more specifically, let you prove that a block header is valid without actually revealing any of the data, right? So you might think, oh well, we have this kind of fancy cryptographic magic. Why don't we just let the cryptographic fancy magic prove for us that all these blocks are valid, and that way we don't need to care about the data? Well, it turns out that even in that case, there are other very nasty things that data unavailability attacks can do. So particularly, if you prevent someone from learning about a transaction, then even if they have the new state root, and even if they have this magic cryptographic proof that the new state root is correct, what they do not have is the entire new state. They have no idea what the balance of certain accounts is. They might be able to download some of the branches, but they're not going to be able to download all of them. And so what a data unavailability attack could do is basically, if it could just prevent people from knowing what the current state of certain accounts is. And what the even nastier thing that happens after that is that if you do not know what the state of some account is, then you cannot create your own transactions that interact with it, right? So the network has, if an attacker makes this one invalid block, this one partially unavailable block, publishes it, and if this gets accepted, then this attacker disappears. All the other participants in the system are not going to be able to agree on blocks that contain transactions that touch these affected accounts because nobody has the information that they need to make a cryptographic proof. So the cryptographic proof could be a Merkle branch, it could be some kind of fancy witness scheme, it could be, it could be whatever. And this applies to Ethereum-like account systems, it applies to Bitcoin-like UTXO systems, it applies to, like basically any kind of design. So does everyone agree that data unavailability attacks are bad? Who here thinks that data unavailability attacks are good? Okay. So the data unavailability problem, right? So incorrectness can be proven even to a light client. And this is basically done with fraud proofs, right? Even if you cannot verify directly, you can always verify indirectly. But data unavailability is not like fraud, or is not like fraud in the sense of creating invalid blocks. And the main difference is the data unavailability is not a uniquely attributable fault. So what do we mean by uniquely attributable fault? Basically, it's a fault where if it happens, you know who did it. Now, with an invalid block, it's totally attributable because if someone creates an invalid block, while there's, in proof of stake, you have a signature attached, or in proof of work, you have kind of this one-time identity with a proof of work solution, and you know that it was this miner that caused the problem, or that it was this validator that caused the problem, and so you can deny them a reward or you can penalize them, and this gives you all the right economic incentives to disincentivize them from doing any sort of nasty stuff. Now, with data unavailability, the problem is basically this. So let's go through two possible cases, and these are just two possible sequences of events that could happen at some point. So here's case one. At time t1, validator v1, who is evil because he has horns. Anyone here have horns and are not evil? Okay, I can be racist against horn people. So validator v1 publishes a block with missing data, right? So validator v1 publishes a block, and this one tiny piece of the block is just not there. It's missing. It has not been published against the network, or published to the network. Time t2, validator v2 raises an alarm, right? It basically says, hey, this piece of data is missing. Look, wah, I'm afraid. At time t3, validator v1 goes ahead and just publishes the remaining data, right? So basically, a validator just says, okay, fine, you raise the alarm, I'm publishing the rest of the thing. Now here's case two. Validator v1, who in this case no longer has horns, publishes a block, and the block actually does contain all of the data. At time t2, validator v2, so the challenger, who is now evil, raises a false alarm. So basically says, look, this data is missing, when it's actually there. At time t3, in this case, validator v1 just does nothing. Now, here's the interesting thing about this story. From the point of view of any client that logs on, or that appears, or that starts paying attention to this piece of data, after time t3, case 1 and case 2 are completely indistinguishable from each other. So after time t3, all that you see is there is a fully published block, and there's an alarm. But you have no idea whether it was case 1 or case 2 that gave rise to the situation. So this leads to something that I call the fisherman's dilemma. And it's called the fisherman's dilemma basically because fisherman is a technical term for specialized nodes in the network that do this. Right? So the fisherman's dilemma basically says, let's suppose that we are living in case 1. What is the expected return of validator v2? And there's literally 3 cases, right? There's 3 kinds of real numbers. So there's real numbers corresponding to people who can count and real numbers corresponding to people who can't. That was a joke. No, so there's real numbers greater than 0, real numbers equal to 0, and real numbers less than 0. So first of all, real numbers greater than 0, right? So what if the expected return of v2 is positive? In this case, what this actually means is that there is a money pump vulnerability, right? So what the money pump vulnerability means is that in case 2, basically validator v2 also makes a profit. And so what this means is that there's profit to be made by just going around and raising false alarms all over the place. This is bad. Now let's say it equals 0. Well, if it equals 0, then there's no money pump vulnerability, but what there is a denial of service vulnerability. Because validator v2 can just raise alarms for every single chunk of every single block of data until everyone is forced to download everything. And if everyone is forced to download everything, then that contradicts our goal of scalability because, we're assuming that each individual client has OFC resources and they're being forced to download more than OFC data if the blockchain's capacity is more than OFC. The other case is the expected return is less than 0. So v2 loses. Now that's good in case 2 because, it means that it's costly to do this kind of attack. But in case 1, what this means is that there's no incentive first of all, there's no incentive to raise the alarm. And second of all, there's a disincentive against raising the alarm. And so what an attacker can do is basically they can just keep on publishing blocks with missing data. They can let the altruistic challengers keep challenging. Then they can just outlast the altruistic challengers. They can just wait until the altruistic challengers run out of money. And when they run out of money, they can keep publishing blocks with missing data, and these blocks could be valid or invalid, and the clients will just give up and accept them. So this is kind of, why a fraud-proof-like approach to data availability is just not going to work. So there's two main categories of solutions to this. The first category is you rely on an honest majority assumption, and you use random sampling. So basically the idea is that you can imagine a blockchain that's kind of, a sharded blockchain. So you would have 100 different kind of universes, and these would be 100 separate sets of accounts. And within each universe, you would also have 100 separate groups of transactions. And you would just randomly assign some group of validators to verify validity, or even just verify availability of, let's say, everything on shard 1 or everything on shard 2, or you might create a committee for shard 43, basically create a separate committee for each individual shard, right? Or for each individual kind of universe of accounts and transactions. Then basically everyone would just trust the committee, right? So each committee would be responsible for downloading all of the data. And if the committee says that the data is available, then we basically just trust that the data actually is available. So this is one solution, but this crucially relies on an honest majority assumption. The other kind of solution basically has to do with the client-side random sampling. So with client-side random sampling, the idea basically is, you have this big hunk of data, and each individual client only has the root hashes of the data. And so the client basically tries to determine if the data is available by doing random sampling, right? So you just randomly select a bunch of indices, try downloading some transactions that have those indices, just randomly pick index number 623, try to download transaction number 623, pick index 285, try to download transaction 285, do this 100 times. If this passes, then it looks like all the data is available. So this works well against attackers that try to withhold all of the data, or against attackers that try to withhold half of the data. What it does not work well against is attackers that try to withhold a tiny piece of data, right? So if an attacker withholds only one single transaction, then this kind of random sampling is not going to work. And so you're basically going to have to, a client is going to have to download everything in order to verify that there isn't a single missing transaction. And as we all know, a single missing transaction is basically enough to completely wreck the system, right? Because with a single missing transaction, that transaction could be an invalid transaction, and I could give myself 50 million Ether. Fortunately, we have erasure codes, error correcting codes, basically a bunch of fancy math that specializes in turning 100% availability problems into 50% availability problems. So the usual mathematical explanation I give for this is, if you have a piece of data, then you can encode the data as 2 points. So you can encode the data as 2 points that you would put on a plane. You draw a line going between those 2 points, then take a bunch of other points on that line. So any 2 points on that line are enough to reconstruct the original line, and therefore any of those 2 points are enough to reconstruct your original data. So this is how you solve a kind of 2 of 2 problem, or you turn a 2 of 2 problem into a 2 of 4 problem. Now, if you go from lines to high degree polynomials, then instead of it being 2 of n, you can make it be 1,000 of 2,000, or 10,000 of 20,000, or like whatever exponents you want, right? So basically the idea here then is that, basically if you have a block where you have some transactions, and the transactions would form a Merkle tree, then you would just make another Merkle tree out of this extra data that gets added. So you can think of this as being like these extra points on a polynomial, and any 50% of all these values together are enough to recover the original data. And so clients can just sample for this to determine sample through this in order to kind of probabilistically get an idea of availability. Now, in order for this to work, you also need to add another kind of fraud proof. So the other kind of fraud proof would basically say this, or oh look, for this particular block, the erasure code is actually malformed, and it's malformed because, look, if you actually try to reconstruct the whole thing, then you get an inconsistency. But if you have that, then you can kind of use this mechanism to verify that that data actually is available. This is kind of similar to proofs of retrievability, and a lot of similar math is used, but the main difference here is basically that in a proof of retrievability, it's Alice sends Bob a file, and then Bob, and we assume that Alice is trusted, so we assume that whoever creates the file is trusted, and they're the ones that send a challenge, or possibly a third party that sends a challenge, and Bob has to reply back with a valid response. Here, the main difference basically is that the person who is creating and uploading the file is also untrusted. So, but, or alternatively, in this case, Alice is Bob. But you have third parties, and arbitrary third parties, that want guarantees about the availability of the file, and about the well-formedness of the erasure code, and also about, is the file actually correct according to the rules of the protocol. There are actually some, it is kind of computationally viable. A lot of this still can be improved much more, but, it's, another important kind of path forward is trying to combine a lot of this stuff with zero-knowledge proofs, because with zero-knowledge proofs you can remove the need for fraud proofs. So this is a kind of more high-tech direction for verifying data availability that doesn't rely on trust assumptions as much. Now, my opinion is that if you want a maximum security solution, then you can basically layer these two schemes on top of each other. And so you can say, a regular node should accept a block as finalized if number one, the committee says it's okay, and number two, it's valid, and number two, the sampling says the data is available, and number three, it hasn't seen a fraud proof yet. So if all three of those checks pass, then that gives you quite a strong guarantee that the data actually is available and valid. So this is probably the closest that it seems like you could get to kind of verifying availability and correctness of data much larger than OFC with only OFC resources. I mean, but so basically with this kind of technique, you can you could imagine a blockchain where the total capacity of the you also have a sharded system, so the kind of transactions are split into these different universes, so it can be executed in parallel on different nodes. And the total capacity of the chain might be something like OFC squared, because you have OFC different shards, and then each shard has OFC capacity, and then you have like a top level mechanism that keeps track of all the shards, so you have OFC of those in total. And then, but where each individual node does not needs to have more than OFC processing power, and where individual clients also do not need to have more than OFC processing power in order to verify any one particular shard. Now, so this is like, if you want to increase the kind of base layer capacity of a chain from OFC to OFC squared, and do so while preserving all these these kind of decentralization and security properties, this seems like the sort of direction that it makes sense to go in, at least if you want to guarantee availability and correctness. So thank you.